Let's go ahead and do some more examples that involve integration by parts. We're going to do the integral of cosine of the cube root of x dx. This one's actually going to start with a u substitution. I'm going to go ahead and let u equal the cube root of x. And then instead of differentiating right away, I'm going to go ahead and cube both sides. So I have u cubed is equal to x. And now I'm going to differentiate both sides and end up with 3u squared du is equal to just 1 dx or dx. Now let's go ahead and make our substitution. We're going to have the integral of cosine of u, and then I'm going to replace dx with 3u squared du. So we've done our change of variables. Hopefully you can start to see how integration by parts is now needed. I'm going to rewrite it as 3u squared cosine u du. And integration by parts is actually needed twice. We're going to perform it twice, and the nice method for that is using the tabular method, or sometimes it's called the DI method. So I'm going to create two columns. Since the variable involved is now u, I'm not going to pick u and dv. I'm going to go ahead and do something like pick k and dv. So for my k, I'm going to pick 3u squared. I'm going to pick the polynomial, which I know will eventually differentiate to 0. And for dv, I'm going to pick cosine u du. And so again, the left column is the differentiate column, and we're going to differentiate in this case until I get to 0. So the derivative of 3u squared is 6u. Derivative of 6u is 6. Derivative of 6 is 0. Down the other column, I'm going to integrate. So the antiderivative of cosine u is sine u. The integral of sine u is negative cosine u. And the integral of negative cosine u is negative sine u. All right, and so here the diagonals are going to be just the answer, but we have to account for the sign. So the first diagonal, all the signs actually stay the same here. But in the second diagonal, we're going to go ahead and multiply in a negative. So ultimately, this negative and this negative will cancel and be positive. And then in the next diagonal, all those signs are going to stay the same because multiplying in a positive doesn't change anything. All right, so now the answer here is going to look like that first diagonal, 3u squared multiplied by sine u. Then the next diagonal is going to end up being positive 6u cosine u. And then minus 6, minus 6 sine u, multiplying these. And then we have plus our constant c. But our original integrand was in terms of the variable x, so we're going to go ahead and substitute the cube root of x back in for u. So we're going to have 3 and then the cube root of x squared sine of the cube root of x plus 6 times the cube root of x cosine the cube root of x minus 6 sine of the cube root of x plus c. And so we can go ahead and leave this as our final answer. In this example, we have the quantity sine inverse of x all squared dx. Similar to the last example, what we're going to do is start with a u substitution. So we're going to let u equal sine inverse of x. And then instead of differentiating right away, because the derivative is 1 over the square root of 1 minus x squared, and we don't have that at all, we're actually going to take sine of both sides. And that's going to leave us with sine of u is equal to, well, if I have sine of sine inverse of x, that's just x. So we have sine of u is equal to x. Now, if I differentiate both sides, the derivative of sine u is cosine u du. The derivative of x is 1, so just dx. All right, so now let's perform our change of variables. So we have the integral of just u squared And then dx is cosine u du. So we have cosine u du. And once again, this calls for integration by parts. It's a repeated parts. This is u squared. And so it's a good candidate for that same tabular method. And I really do mean same tabular method. So I'm going to say let k equal u squared. And then dv is equal to cosine u du. And so we're going to differentiate until we get to 0. So slightly different. So derivative of u squared is 2u. Derivative of 2u is 2. Derivative of 2 is 0. But this column here is the same as the last one. So the integral of cosine u, sine u, integral again, negative cosine u, integral again, negative sine u. Those diagonals have to alternate the signs across the diagonals, right? Putting in positive, negative, positive. And then we can go ahead and go straight to our answer here. So we're going to have u squared sine u, and then plus, since these two negatives are going to make a positive, 2u cosine u, and then minus 2 sine u plus c. But we are going to have to return to x, so replace each of our u's with that sine inverse of x. All right, by the magic of video recording, here we have all of the u's with sine inverse of x substituted in. There is some simplifying that we want to go ahead and do. So here, when we substituted in sine inverse into this u, we have sine of sine inverse of x. So that's going to simplify to just x. And then here we have a cosine of sine inverse of x. So we can actually do something with that. We'll do that in just a moment. And then over here we have that sine of sine inverse of x again, which simplifies to just x. So each of these right here is going to simplify to just a single x. But this part right here, cosine of sine inverse of x, this is more of a trig review than anything else. We're going to pull that off to the side and think about how we can turn that into an algebraic expression. All right, so here let's just look at cosine of sine inverse of x. So when we think about an inverse trig function, what we're thinking usually is, that the answer is an angle. So let's take a second and just say sine inverse of x is some angle theta. Okay, so sine inverse of x is equal to theta. Well, then if I take sine of both sides, I'm going to get the fact that x is equal to sine of theta, or x over 1 is equal to sine of theta. And from there, what I want to do is create a right triangle. If sine of theta is x over 1 in a right triangle, we can say that the opposite side of theta is x, and the hypotenuse is 1. Sine is opposite over hypotenuse, sine is x over 1. All right, how does that help us? Well, if we said sine inverse of x is theta, then this entire expression is really just asking us for cosine of theta. All right, well, on a right triangle, what is cosine? Cosine is the adjacent side over the hypotenuse. So as long as we can find this adjacent side represented as a function of x, then we can find cosine of theta. Well, how do I find the missing side of a right triangle? The Pythagorean theorem. So let's go ahead and take a second and call this b. I'm looking for b, so what do I know? I know b squared plus x squared must be equal to 1. The two side lengths squared are equal to 1. I'm solving for b. So b squared is 1 minus x squared. And so, b is equal to plus or minus the square root of 1 minus x squared. Well, we're going to go ahead and assume the positive value here. So we're going to say this side length is positive the square root of 1 minus x squared. Where does that leave us? We wanted cosine of sine inverse of x, which we said is cosine of theta. Well, cosine of this theta is adjacent over hypotenuse. So this is equivalent to the algebraic expression radical 1 minus x squared over 1, right? Which is just the square root of 1 minus x squared. So I can replace this composition this trig composition with an algebraic expression. And in general, that's nicer, right? That's simpler. So let's go ahead and write out our final answer here. We'll have sine inverse of x squared times x. So sine of sine inverse of x is just x. So this is times x plus 2 sine inverse of x, and then times the square root of 1 minus x squared minus 2x plus c. In this example, we have the integral of e to the 4x times sine of x over 2 dx. And this is a classic integration by parts problem that we want to recognize ends up being circular. And so because we want to be able to recognize that, and we know what the process is going to be, and that it's going to require integration by parts twice, we can actually use the tabular method as long as we know how to use it. So on this one, what I'm going to do is I'm going to go ahead and let u equal e to the 4x and dv be sine of x over 2 dx. And in all honesty, it doesn't matter which one you pick as u and dv in this particular problem. And so we know we have to do integration by parts twice, exactly twice, just because of the structure of the problem. And so what we're going to do is differentiate twice and integrate twice, because neither of these, if we pick them for u, would ever differentiate and terminate to 0. So we're going to take the derivative of e to the 4x, that's 4 e to the 4x, and the derivative again is 16 e to the 4x. And then we're going to integrate sine of x over 2. So the antiderivative is going to be negative cosine of x over 2, but we need, there's a 1/2 in front of this x, so the reciprocal of that is 2. So we're going to have negative 2 cosine of x over 2. And then we're going to integrate again, and another 2 is going to pop out. So we're going to have negative 4 and then sine of x over 2. So make sure you know your general antiderivatives. So again, we differentiated twice, we integrated twice, and now the diagonals are part of the answer, and we're still going to have to say the first diagonal is positive, and the second one we're going to multiply in an extra negative. But now what we have to do is consider this horizontal, because normally in the tabular method, this is a 0. But now this is not a 0, so this, when you go horizontal, now that's going to be an integral. So let's go ahead and rewrite the entire problem again. So we have the integral of e to the 4x sine of x over 2 dx is equal to, okay, so this is part of the answer when I multiply this first diagonal. So I'm going to have negative 2 e to the 4x cosine of x over 2. And then this diagonal is part of the answer. The two negatives multiply and become positive. So we have positive 16 and then e to the 4x sine of x over 2. But this horizontal is an integral still. So I'm going to take the coefficient out of the integral. So that's 16 and negative 4. So if I multiply that together, it's going to give me a negative 64. So I'm going to have negative 64, the integral of e to the 4x sine of x over 2 dx. Now what we want to notice is that we went in a circle. So our original integrand, e to the 4x sine of x over 2, is over here, e to the 4x sine of x over 2. And so the strategy is that we add 64, the integral of e to the 4x sine of x over 2, to both sides of this equation. So it's a like term, basically. We're going to add these integrals as they are like terms. So we're performing this addition here. And so there's a 1 in front of this original integral, right? And so when we add those numbers in front of the integral, we're going to have 65, the integral of e to the 4x sine of x over 2 dx is equal to, and now these just come down. So we have negative 2 e to the 4x cosine of x over 2 plus 16 e to the 4x sine of x over 2. And the negative and the positive over here are gone. So I have 65 copies of the integral that I wanted. Well, I just wanted one copy of it, so I'm going to divide by the 65 over here. All right, I made myself some space. So now what we end up with is the integral of e to the 4x sine of x over 2 dx is equal to negative 2 over 65 e to the 4x cosine of x over 2 plus 16 over 65 e to the 4x sine of x over 2. And then I don't want to forget my generic constant c. So we have this whole thing as the final answer to our original problem. So we can use the tabular method to keep our work a little bit more organized, but we had to know walking in that when we have an exponential times sine or cosine, that particular form ends up becoming that circular method problem, and so we know exactly what to do, and we're just making good use of the tabular method to shorten our work. Now let's integrate secant cubed x dx. And it's actually kind of deceiving. Let's take a minute to think about if this was the integral of secant squared x dx, that's a really easy problem. The integral of secant squared x is just tangent x. And if we're integrating secant x, that one's a little trickier. If you've worked through this one, you know it's an interesting u substitution. And we generally memorize the result. It's the natural log of the absolute value of secant x plus tangent x plus c. But secant cubed x is actually going to take a little bit of work here. The first thing we want to do is actually break it down and rewrite it as the integral of secant squared x times secant x dx. But then we don't want to go crazy. We cannot integrate each one separately, so we don't want to say it's just these two answers multiplied together or anything. But now what this does is give us a u and a dv situation. So back up here, I mean, we could have chosen u to be secant cubed x and dv to be dx, but that actually would not have helped us. So what now that we've broken it up, we are going to go ahead and let u be secant x, whoops, and dv be secant squared x dx. Now, why did we do that? Keep in mind, we have to integrate secant squared x. And we just said over here, the integral of secant squared was really nice. It was just tangent. And then we differentiate secant x. So here, du, derivative of secant, is secant x tangent x dx. And again, the integral of secant squared x, so v, is just tangent x. Okay, so now we're going to go back to sort of that traditional version of integration by parts where we multiply u times v and then minus the integral of v du. So this integral now, so far, is secant x tangent x minus the integral of, if I multiply these two together, I'm going to have secant x times tangent squared x dx. All right, so from here, how am I going to integrate what's left over? So we can't actually do a u substitution. It's not really going to work. If I let u be tangent, the derivative is secant squared. I don't have that. If I let u be secant, the derivative is secant tangent. I'll have an extra tangent. So what we're going to do is we're going to use a Pythagorean identity on this. We're going to rewrite tangent squared x as secant squared x minus 1 dx. And then I'll bring down the secant x tangent x. Okay, so how does that help us? Now, if I distribute the secant x, I have secant cubed x, and then minus secant x dx. All right, so what happened? I did a bunch of work. And I ended up getting, at least in part inside this integrand here, the original thing I was trying to integrate. I went in a circle. So this one actually happens to be a circular method problem as well, similar to the last one, but we didn't recognize it right away. So we just went for a more traditional route. So now let's kind of keep going with it. Let's say this is secant x tangent x minus the integral of secant cubed x dx. And then this negative, or this minus, and this here will distribute and give us a positive, the integral still, of secant x dx. And so what is all of this equal to? It was equal to this original problem up here. So I'm going to rewrite it. The integral of secant cubed x dx. So we're going to do that same idea where I'm going to think about this as a like term to this one, and I'm going to add it over to the other side. All right, making some more space for ourselves. So we're going to add secant cubed x dx plus the integral of secant cubed x dx. And so here there is a 1 in front and a 1 in front. So I have 2 copies of the integral of secant cubed x dx. We'll bring this down. That's just secant x tangent x. These cancel because we have -1 and +1. And we still have the integral of secant x to deal with. But we talked about that at the very beginning. We typically memorize the result of that. And so that's going to be plus the natural log of the absolute value of secant x plus tangent x. I'm going to go ahead and not put the plus c yet. I'm going to save it for the end. And then here we're going to divide by that 2. So we're going to have the integral of secant cubed x dx is equal to, if I divide by 2, it's like multiplying by a half. So 1/2 secant x tangent x plus 1/2 natural log the absolute value of secant x plus tangent x, and then plus c. I didn't want to bother with putting a plus c right here. You know, when you divide by a generic constant by 2, it's still a generic constant. So I just want to remember to throw it in at the end. So here we have our answer. Now, this is a result that sometimes can also be worth memorizing because when we're doing some later integrals, secant cube tends to come up in parts of other problems. And so it might seem kind of hard to memorize this, but I'm going to try to give you a shortcut for it. So if we remember, the derivative of secant is secant tangent, and then the integral of secant, regular secant, is natural log of absolute value of secant x plus tangent x. This is just the sum of the derivative and the integral of secant x, but with a 1/2 in front. So I think that's maybe a little bit helpful to know. The integral of secant cubed x in particular is 1/2 the derivative of secant plus 1/2 the integral of secant, and then of course plus c. Now I just want to briefly show there is a reduction formula for when n is greater than 1 if we want to integrate secant x raised to the nth power dx. So it's this, big formula here. But let's just take a look at how it works if we did memorize it to do an integral like the one we just did, secant cubed x dx. All we need is that power of n, which is 3, and to substitute it into all the n's in this formula. So 1 over 3 minus 1 is 2, so 1/2. And then secant to the 3 minus 2, that's 1, so just secant x tangent x. And then right here, plugging in n, which is 3, into these n's, 3 minus 2 is 1. 3 minus 1 is 2, so we get plus 1/2 the integral of secant to the 3 minus 2, that's 1, so the integral of secant x dx. Well, we already know the integral of secant x is natural log, absolute value, secant x plus tangent x. Bring everything else down, we get the same result. But again, it also works for higher powers. We just have to memorize it. But let's try it one more time for a higher power. So let's say the integral of secant to the 4th x dx. So our n is 4. 1 over 4 minus 1, we have 1/3. Secant to the 4 minus 2, that's 2. Secant squared x tangent x plus 4 minus 2 over 4 minus 1 is 2/3. The integral of secant to the 4 minus 2, that's 2, secant squared x dx. And we already know the integral of secant squared x is tangent x. So we have our final answer once we just go ahead and do that final integration piece.